If the future already exists, why do we experience motion? You are hurtling through space at roughly 108,000 kilometers per hour. That is the speed at which our planet orbits the sun. On top of that, the solar system itself is sweeping around the center of the Milky Way at about 828,000 kilometers per hour, and the galaxy itself is barreling through the cosmos at millions of kilometers per hour relative to the cosmic microwave background. You are moving unimaginably fast right now. But here is the strange part. Close your eyes for a moment and try to feel that motion. Try to feel the Earth spinning on its axis at over 1,600 kilometers per hour at the equator. Try to feel the solar system's spiral through the galactic arm. Try to feel the Milky Way's headlong rush through the void. You feel nothing. Absolute stillness. The coffee in your cup sits calmly. The air in the room is motionless. Your body registers no acceleration, no tug, no spin. You are riding a cosmic roller coaster at absurd velocities, and your senses detect none of it. Already, before we have said a word about physics or philosophy, your direct experience of motion has proven itself to be an unreliable guide to what is actually happening. And yet, according to some of the most brilliant physicists who have ever lived, none of that motion is real, not in the deepest sense. According to one interpretation of our most successful theory of space and time, you are not actually going anywhere. You have never gone anywhere. Because the place you will be tomorrow and the place you were yesterday both exist right now. They have always existed. They always will. Your birth, your death, and every single moment in between are all equally real, all frozen in place, like frames of a movie reel that nobody is projecting. The film just sits there, complete, every scene already shot, every ending already written. If that sounds impossible, if it offends every fiber of your being, you are in excellent company. This idea has been debated, defended, and attacked by some of the greatest minds of the 20th and 21st centuries. Albert Einstein believed in it. So did his former teacher Hermann Minkowski. The Nobel laureate Roger Penrose has used it to craft one of the most unsettling thought experiments in all of physics. And yet, other brilliant physicists, like Lee Smolin, have dedicated their careers to dismantling it, arguing that this frozen picture of reality is not just wrong, but dangerously misleading. The idea is called the block universe. And the question it raises is, quite possibly, the most intimate scientific question you will ever encounter. Because it does not ask about black holes or distant galaxies. It asks about you, about the experience of being alive, about the sensation happening inside you at this very moment of time passing, of 1 second becoming the next, of motion and change and the feeling of traveling forward through your life. If the future already exists, fixed and immutable, sitting out there in the geometry of space-time waiting for you to arrive, then why does it feel like you are moving toward it? Why do clocks tick? Why do you age? Why can you remember yesterday, but not tomorrow? Why does existence feel like a river carrying you forward when the mathematics of physics suggests it is more like a frozen lake? This is not philosophy dressed up as physics. This is a question that emerges directly from the equations that govern the universe. And as we will see, the answer, or the many competing answers, will take us from Einstein's study in Bern to the quantum foam at the smallest scales of reality, from the thermodynamic engines of the Industrial Revolution to the neural circuitry inside your own skull. The question of why we experience motion, if the future already exists, is a thread that, when pulled, unravels almost everything we think we know about reality. Let us begin by pulling it. There is a story, possibly apocryphal, but too good not to tell, about a conversation between Albert Einstein and the family of his lifelong friend, Michel Besso. Besso had died in March of 1955, just a few weeks before Einstein himself would follow. In a letter of condolence to Besso's family, Einstein wrote something remarkable. He said that the distinction between past, present, and future is only a stubbornly persistent illusion. This was not a poetic flourish from a grieving old man. Einstein meant it literally. He had believed it for half a century, and he believed it because his own theory of relativity demanded it. To understand why, we need to go back to the world before Einstein, to the physics of Isaac Newton. And to do that, we need to understand the radical simplicity of Newton's picture of the universe, a picture that dominated science for more than 200 years. And that still shapes the way most people, most non-physicists, think about time. In Newton's universe, time was simple. It flowed. It flowed uniformly everywhere for everyone, like an invisible river carrying the entire cosmos forward at the same steady rate. Newton wrote in his Principia, the foundational text of modern physics, that absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. A clock in London ticked at the same rate as a clock in Beijing, as a clock on Jupiter, as a clock at the edge of the observable universe. Time was a stage, and the events of the universe were actors performing upon it. The stage itself was unchanging, unyielding, indifferent to whatever dramas played out upon its surface. This was more than a convenience. It was an axiom, a bedrock assumption upon which the entire edifice of Newtonian mechanics was built, and that edifice was magnificent. With his laws of motion and his law of universal gravitation, Newton could predict the motions of planets, the trajectories of cannonballs, and the orbits of moons. He could explain the tides and the precession of the equinoxes and the paths of comets. For over 2 centuries, Newton's physics was the gold standard of scientific achievement, a monument to the power of human reason. But by the late 1800s, cracks had begun to appear. The Scottish physicist James Clerk Maxwell had unified electricity and magnetism into a single theory, and his equations predicted electromagnetic waves that traveled at a specific speed, the speed of light. But Maxwell's equations did not specify what this speed was relative to. If light were a wave, what was it waving in? Physicists posited a medium, the luminiferous ether, a substance that permeated all of space and served as the reference frame for light's motion. In 1887, the American physicists Albert Michelson and Edward Morley attempted to detect the ether, by measuring the speed of light in different directions. If the Earth were moving through the ether, they reasoned, then light traveling in the direction of the Earth's motion should appear to move at a slightly different speed than light traveling perpendicular to it. The result was one of the most famous null results in the history of science. They found no difference. The speed of light was exactly the same in every direction, regardless of the Earth's motion. The ether did not exist. Other physicists, notably the Dutchman Hendrik Lorentz and the Frenchman Henri Poincaré, proposed mathematical adjustments to account for this result. Lorentz introduced his transformations, equations that described how lengths and times changed for moving objects. Poincaré recognized the deep symmetry principles at work. But it was a 26-year-old patent clerk in Bern, Switzerland, who saw through to the heart of the matter. Albert Einstein decided to take the experimental fact of the constancy of the speed of light at face value. Rather than trying to explain it away, he accepted it as a fundamental truth about the universe and asked what would follow. What followed was the special theory of relativity, published in 1905 in a paper modestly titled On the Electrodynamics of Moving Bodies. And it demolished Newton's absolute time. Einstein showed that time does not flow at the same rate for everyone. If you are moving relative to me, your clocks tick more slowly than mine, an effect called time dilation. This is not a matter of perception or measurement error. It is a genuine feature of the universe. Time itself slows down for moving objects. The effect is tiny at everyday speeds, but it has been confirmed thousands of times experimentally. In particle accelerators, unstable particles called muons, which should decay in millionths of a second, live much longer when traveling close to the speed of light. Exactly as relativity predicts, GPS satellites, which orbit at high speeds and in weaker gravitational fields, must correct for relativistic time dilation, or their position estimates would drift by about 10 kilometers per day. The technology in your pocket works because Einstein was right. But Einstein's former mathematics teacher, Hermann Minkowski, saw something even deeper lurking in the equations. Minkowski had once dismissed Einstein as a lazy dog, but when he read the special relativity paper, he was stunned by what his former student had accomplished. In September of 1908, speaking to the German Society of Scientists and Physicians in Cologne, Minkowski presented a geometric reformulation of Einstein's work that would change our understanding of reality forever. He opened with words that have become some of the most quoted in all of physics. He said that the views of space and time, which he wished to lay before the audience, had sprung from the soil of experimental physics, and therein lay their strength. And then he made his fateful declaration. He said that henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. That union was spacetime. In Minkowski's formulation, the universe was not a three-dimensional stage on which events played out over time. It was a four-dimensional object, a single entity with 4 dimensions, 3 of space and 1 of time. Events were not things that happened at a place and then disappeared into the past. Events were points in four-dimensional spacetime, fixed and permanent, just as a point in ordinary three-dimensional space has an x-coordinate, a y-coordinate, and a z-coordinate. An event in spacetime has three spatial coordinates and one temporal coordinate, and just as every point in three-dimensional space exists, whether or not anyone is standing there, every event in four-dimensional spacetime exists, whether or not anyone is experiencing it. Einstein initially dismissed Minkowski's formulation as unnecessary mathematical embellishment. He reportedly called it superfluous learning. But within a few years, as he labored to extend special relativity into a general theory that included gravity, he realized he could not do it without Minkowski's four-dimensional framework. General relativity, Einstein's masterpiece completed in 1915, describes gravity not as a force pulling objects together, but as the curvature of four-dimensional spacetime caused by the presence of matter and energy. The great physicist John Archibald Wheeler would later summarize the theory with elegant simplicity. Matter tells spacetime how to curve, and curved spacetime tells matter how to move, and the spacetime in question is Minkowski's four-dimensional block. It was one of those rare moments in the history of science when a teacher's insight proved essential to the student's greatest achievement. Einstein had dismissed Minkowski's work, then been forced by the logic of his own theory to adopt it completely. Minkowski, tragically, did not live to see this. He died of appendicitis in January of 1909 at the age of 44, just 4 months after delivering his famous lecture. But his vision of the universe as a four-dimensional block endures. So what does it mean, concretely, to say that the universe is a four-dimensional block? Let us try to build an intuition for this strange and counterintuitive idea. Imagine slicing a loaf of bread. Each slice represents a single moment in time, a snapshot of the entire universe frozen at one instant. The bread itself, the full unsliced loaf, represents all of spacetime. Every slice, every moment, past, present, and future, is already there, baked into the loaf. You do not need to add new slices. You do not need to remove old ones. The loaf is complete. In this picture, which physicists and philosophers call the block universe or eternalism, there is no special moment called now. Your experience of the present moment is not a spotlight sweeping across the loaf, illuminating one slice at a time. Instead, every slice is equally illuminated. Every moment is equally real. The Big Bang is just as real as the heat death of the universe. Your birth is just as real as your last breath. They are all there, all at once, embedded in the geometry of the four-dimensional block. This idea has ancient roots, stretching back further than most people realize. The Greek philosopher Parmenides, writing in the 5th century before the Common Era, argued that change is an illusion and that reality is timeless, unchanging, and eternal. His student Zeno devised a series of famous paradoxes, like the paradox of Achilles and the tortoise, designed to show that motion is logically impossible. For 25 centuries, these ideas were considered interesting, but unscientific, philosophical curiosities with no connection to the physical world. Then Einstein came along, and to the astonishment of everyone, showed that Parmenides might have been onto something. The modern argument for eternalism does not rest on ancient philosophy, however. It rests on the mathematics of special relativity, and specifically on one of its most counterintuitive consequences, the relativity of simultaneity. This is the feature of Einstein's theory that transforms the block universe from a philosophical speculation into a near inescapable conclusion, and it requires some careful explanation. In Newton's universe, simultaneity was absolute. If two events happened at the same time, they happened at the same time for everyone, regardless of how fast they were moving or where they were located. This seems so obvious that it hardly needs stating. If two bombs explode at the same instant, they explode at the same instant, period. What could possibly change that? But special relativity destroys this certainty. Two events that are simultaneous for one observer may not be simultaneous for another observer who is moving relative to the first. This is not a matter of perspective or perception, or the time it takes light to reach an observer's eyes. It is a fact about the geometry of spacetime itself. There is no universal now stretching across the cosmos, and this changes everything. Einstein demonstrated this with one of the most famous thought experiments in the history of physics, involving a train and two lightning strikes. Imagine a train racing along a track at tremendous speed. Lightning strikes both ends of the train at the same instant. According to an observer standing on the platform at the midpoint between the two strikes, she sees both flashes of light arrive at her eyes at the same moment and correctly concludes, since she is equidistant from both strikes and light travels at the same speed in all directions, that the two strikes happened simultaneously. But now consider the observer sitting in the exact middle of the train. He is rushing forward toward the front of the train and away from the back. Since light always travels at the same speed regardless of the observer's motion, this is the fundamental postulate of special relativity. The light from the front strike reaches him slightly before the light from the rear strike, and since he knows he is equidistant from both ends of the train, he is sitting in the middle, after all. And since light travels at the same speed in both directions in his frame of reference, he concludes that the front strike happened first. The two strikes were not simultaneous. They happened at different times. Both observers are correct. Neither is making an error. There is no fact of the matter about which lightning strike happened first. Simultaneity depends on your state of motion. Events that are simultaneous in one reference frame are not simultaneous in another. This is not a flaw in the theory. It is one of its core predictions, confirmed by every experiment ever devised to test it. Now, you might think this is a minor curiosity, relevant only at speeds close to the speed of light, with no bearing on everyday life. In practice, for two people standing on the same street corner, the difference in their definitions of now is so tiny as to be utterly undetectable. But as Nobel laureate Roger Penrose demonstrated with a devastating and now famous thought experiment, the effects of this principle scale up dramatically when you stretch them across the vast distances of the cosmos. Penrose introduced what is now known as the Andromeda paradox in his 1989 book, The Emperor's New Mind. The setup is deceptively simple and devastatingly effective. Imagine two people walking past each other on a street here on Earth. One person, let us call her Alice, is walking toward the Andromeda galaxy. The other, Bob, is walking away from it. They are moving at ordinary walking speed, perhaps 5 kilometers per hour. The difference in their velocities is trivial, the kind of speed difference you would not think twice about. You would not notice it. A physicist measuring their motion would need extremely sensitive instruments to detect it. But the Andromeda galaxy is 2.5 million light years away. 2.5 million light years. That is roughly 23 quintillion kilometers. And over that staggering distance, the tiny difference in Alice's and Bob's velocities causes their planes of simultaneity, their definitions of what is happening now at Andromeda, to tilt relative to each other. The tilt is negligible at nearby distances. At the distance of the Moon, the difference would be measured in nanoseconds. At the distance of Mars, perhaps seconds. But at the distance of Andromeda, 2.5 million light years away, the tiny tilt amplifies into a difference of several days. What this means is deeply unsettling. According to Alice's definition of now, a particular event on a planet in the Andromeda galaxy, say, an alien parliament debating whether to launch an invasion fleet, has not yet occurred. The decision has not been made. The future is open. The aliens are still arguing around their conference table, or whatever their equivalent is. But according to Bob's definition of now, the decision was made 3 days ago. The vote has been taken. The fleet has launched. The ships are already on their way. And here is the part that makes physicists lose sleep. Alice and Bob are standing right next to each other on the same street corner. They are separated by less than a meter. They have this difference in their definitions of reality because one of them is walking 5 kilometers per hour to the left, and the other is walking 5 kilometers per hour to the right. Walking at human speeds. And yet they disagree about the state of affairs at Andromeda by several days. If Alice's now is the real present, then the decision has not yet been made, and the future is genuinely open. If Bob's now is the real present, then the fleet has launched, and the future is settled. But there is no physical reason to prefer one definition over the other. Special relativity treats all inertial frames of reference as equally valid. The principle of relativity itself says that there is no preferred reference frame. Neither Alice nor Bob has a more legitimate claim to defining the present than the other. The only way out, the argument goes, is to accept that both the decided and undecided states are real. Both exist. The alien parliament debating and the alien fleet launching are both out there in the block of spacetime, equally real, equally frozen. The entire history of the Andromeda galaxy, its past, present, and future, all of it exists at once, embedded in the four-dimensional structure of the universe. This is the Rietveld-Putnam argument, named after the Dutch physicist C. W. Rietveld and the American philosopher Hilary Putnam. who independently formulated it in 1966 and 1967, respectively. Penrose's Andromeda scenario is a vivid, visceral illustration of their abstract reasoning. And its conclusion is radical. If the relativity of simultaneity is true, and experiments have confirmed it beyond any reasonable doubt, then the future already exists. It is not open. It is not undetermined. It is already there, as fixed and definite as the past. Not everyone accepts this argument. The philosopher Howard Stein challenged it in 1968, arguing that relativity treats the present as a strictly local concept, and that the thought experiment conflates a mathematical property of spacetime with a metaphysical claim about what exists. The physicist N. David Hermann has stated flatly that no inherent meaning can be assigned to the simultaneity of distant events. But the mathematical structure of special relativity undeniably supports the eternalist interpretation, and many physicists and philosophers find it compelling. The debate remains very much alive. But let us, for now, accept the block universe as a working hypothesis and press forward with our central question. If the future already exists, then why does it feel like it has not happened yet? Why do we experience motion? To answer this, we need to understand how objects exist within the four-dimensional block. And this is where things get genuinely strange, because in Einstein's universe, everything is always moving through space-time at exactly the same speed. That speed is the speed of light. This is one of the most profound and least appreciated results in all of physics, and it deserves careful unpacking. In special relativity, every massive object has what is called a four-velocity. This is a velocity vector that has four components, 3 for space and 1 for time, describing the object's rate of motion through four-dimensional spacetime. The mathematics shows that the magnitude of this four-velocity is always equal to the speed of light. Always. For everything. For a speeding bullet, for a drifting asteroid, for a frozen rock at absolute zero, for you sitting in a chair right now. But wait, you might protest. I am sitting still. I am not moving at the speed of light. And you are correct in three-dimensional space. You may well be motionless with respect to the chair beneath you and the floor beneath the chair, but you are not motionless in four-dimensional spacetime. You are hurtling through the time dimension at very nearly the speed of light. When you sit perfectly still in space, all of your motion through spacetime is directed along the time axis. Your clock ticks at its maximum possible rate. You age as fast as you possibly can. Now imagine you start moving through space. You get in a car and accelerate to highway speed. Some of your motion through spacetime, which was previously directed entirely along the time axis, is now redirected into the spatial dimensions. You are moving through space now, and since your total speed through spacetime is fixed and unchangeable, the portion of that speed available for moving through time must decrease. Your clock slows down. You age slightly more slowly than someone who remains sitting still. This is the origin of time dilation. It is not a side effect or a peculiar anomaly. It is the inevitable and beautiful consequence of the fact that your speed through spacetime is constant. Think of it as a cosmic speed budget. You have a fixed amount of speed to spend, always equal to the speed of light. If you spend more of it on motion through space, you have less to spend on motion through time, and vice versa. The faster you move through space, the slower you move through time. The twin paradox, that famous thought experiment in which one twin travels at near light speed and returns to find her sibling, has aged decades, while she has aged only years, is a direct manifestation of this trade-off. The traveling twin spent more of her space-time speed budget on spatial motion, leaving less for temporal motion. Her clocks ran slower. She aged less. A photon, a particle of light, has taken this trade-off to its logical extreme. It moves through space at the speed of light, meaning it has allocated its entire space-time velocity budget to the spatial dimensions. It has nothing left for the time dimension. From the photon's perspective, if we can even speak of such a thing, no time passes whatsoever. A photon emitted from a star in the Andromeda galaxy 2.5 million years ago and absorbed by your retina tonight experiences no elapsed time between those two events. Its departure and its arrival are, from its own perspective, the same moment. For a photon, the entire history of the universe is compressed into a single instant. This is why we say that light is timeless, not in a poetic sense, but in a precise physical sense. A photon does not age. It does not decay. It does not experience duration. It exists at the boundary of time, at the edge of the permissible geometry of spacetime, where the temporal dimension has been completely traded away for spatial motion. And here is a thought worth sitting with. Every time you look at a star, the photons entering your eyes have made a journey that, from their own perspective, was instantaneous. The light from the sun took about 8 minutes to reach you by your clock, but 0 seconds by the photon's clock. The light from the nearest star beyond the sun, Proxima Centauri, took about 4 years to reach you, but 0 seconds in its own frame. The light from the cosmic microwave background, the oldest light in the universe, has been traveling for over 13 billion years from our perspective. But in its own experience, it was emitted and absorbed in the same timeless instant. The universe, seen from the perspective of light, is a place where everything happens all at once. Now consider something heavier, something more like you. The astronauts aboard the International Space Station orbit the Earth at roughly 28,000 kilometers per hour. That is fast by human standards, but only a tiny fraction of the speed of light. As a result, their clocks tick just slightly slower than clocks on the ground. Over the course of a 6-month mission, they age about 5 milliseconds less than their Earth-bound colleagues. 5 milliseconds. Not much, but it is real, and it accumulates. Cosmonaut Gennady Padalka, who has spent more time in space than any other human, has aged roughly 22 milliseconds less than the rest of us. He is, in a precise physical sense, 22 milliseconds younger than he would have been had he stayed on the ground. At higher speeds, the effect becomes dramatic. If you could somehow accelerate to 90% of the speed of light, your clocks would tick at less than half their normal rate relative to someone who stayed behind. At 99%, they would tick at about 1/7 the rate. At 99.9%, about 1/22nd, and at 99.999999999%, your clocks have practically stopped. You are barely aging at all, while the universe outside your window races ahead at a furious pace. You have redirected almost your entire space-time velocity budget into spatial motion, leaving almost nothing for time. This trade-off between motion through space and motion through time is not a metaphor or an analogy. It is encoded in the mathematics of Minkowski spacetime, in a quantity called the spacetime interval. The interval between two events is invariant, meaning all observers agree on its value, even though they may disagree about the individual spatial and temporal separations. It is this invariance that gives spacetime its geometric structure and makes the block universe picture so compelling. So when you feel yourself moving through time, when you feel the seconds ticking by and the minutes accumulating and the hours passing, what you are actually experiencing is your world line. Your world line is the path traced by your existence through four-dimensional spacetime. It extends from your birth at one end to your death at the other. Every event in your life, every conversation, every meal, every sunrise is a point along this world line. And in the block universe, every one of those points already exists, embedded in the geometry of the block. You are not traveling along your world line the way a car travels along a highway. In the block universe picture, there is no motion along the world line. You are your world line. Every version of you at every age, at every moment, is equally real. The you who is reading these words right now is no more and no less real than the you who ate breakfast this morning, or the you who will fall asleep tonight, or the you who existed as a child. They are all there, all at once, all equally embedded in the frozen geometry of spacetime. This is what Einstein meant when he said the distinction between past, present, and future is an illusion, not a mistake, not a failure of reasoning, but an illusion in the deepest sense, a feature of our conscious experience that does not correspond to any feature of the external physical world. But if the block universe is frozen, if nothing truly moves, if the future already exists and the past never disappears, then we are left with a profoundly uncomfortable question. Why does the universe have a direction? Why does time seem to flow in one direction and not the other? Why do eggs break but never unbreak? Why do we remember the past but not the future? If the laws of physics are time-symmetric, if they work equally well in both directions, then what gives time its arrow? The answer, or at least the best answer we have, does not come from relativity at all. It comes from a completely different branch of physics. It comes from thermodynamics, the science of heat and energy and disorder, born not in the serene halls of a university, but in the sweaty, coal-dusted factories of the Industrial Revolution. In the early 1800s, a young French military engineer named Nicolas Leonard Sadi Carnot became fascinated by the steam engines that were transforming the face of Europe. These massive, clanking, coal-burning machines were driving the factories and railroads that were reshaping society. And Carnot wanted to understand the fundamental limits of their efficiency. How much useful work could you extract from a given amount of heat? Was there a theoretical maximum? In pursuing this seemingly practical question, Carnot stumbled upon a truth far more profound than anything to do with engines. He discovered that there is a fundamental asymmetry in the behavior of heat. Heat flows naturally from hot objects to cold objects, but never the other way around. You can hold an ice cube in your warm hand, and your body heat will melt the ice. But you will never see heat flowing out of a cold glass of water to make your hand warmer. A cup of hot coffee left on a desk will cool down to room temperature. But a cup of room temperature coffee will never spontaneously heat itself up by extracting warmth from the cooler surrounding air. This principle was formalized over the following decades by physicists, including Rudolf Clausius and Lord Kelvin, into what we now call the second law of thermodynamics. Clausius introduced the concept of entropy, a quantity that he showed always increases in an isolated system. He expressed this with poetic grandeur. The entropy of the universe tends to a maximum. In the 1860s and 70s, the Austrian physicist Ludwig Boltzmann gave this law a deeper, statistical interpretation that connected the macroscopic world of heat engines to the microscopic world of atoms. Boltzmann was a man of passionate convictions and melancholic temperament, a physicist who saw further into the nature of entropy than anyone of his generation, and who paid a terrible price for it. He was born in Vienna in 1844 and spent his career defending the atomic theory of matter at a time when many prominent scientists, including the influential Ernst Mach, doubted that atoms even existed. The opposition was fierce, and it wore on him. But Boltzmann's insight was profound, and history has vindicated him completely. He showed that entropy is fundamentally a measure of probability, a count of how many different microscopic arrangements of particles are consistent with the macroscopic state we observe. A hot cup of coffee in a cold room has low entropy because there are relatively few ways for the molecules to be arranged, so that all the fast-moving, energetic ones are confined to the cup, and the slow-moving ones are in the surrounding air. A lukewarm room where the coffee has cooled to room temperature has enormously higher entropy because there are astronomically more ways for the molecules to be spread out with roughly equal energies everywhere. Think of it this way. Imagine you have a box divided in half by a partition, with all the air molecules crammed into the left half and a vacuum in the right half. Now remove the partition. What happens? The gas rushes to fill the entire box, and within moments, it is evenly distributed. This outcome is not driven by any force. No invisible hand is pushing the molecules to the right. It happens simply because there are overwhelmingly more ways for the molecules to be spread throughout the entire box than to be concentrated on one side. If each molecule can be on either side, and you have a trillion molecules, the number of arrangements in which they are roughly evenly distributed is so staggeringly vast compared to the number of arrangements in which they are all on one side that the probability of a spontaneous return to the all-on-one-side configuration is essentially zero, not literally zero. Just so improbable that you would have to wait far longer than the age of the universe to see it happen even once. Boltzmann captured this idea in a deceptively simple equation, now carved on his gravestone in Vienna's Central Cemetery. The equation relates entropy to the number of microscopic states compatible with a given macroscopic description. It is one of the most important equations in all of physics, a bridge between the world of atoms and the world of engines, between the reversible and the irreversible, between the timeless laws of microscopic physics and the error-laden laws of thermodynamics. Boltzmann himself did not live to see the full vindication of his ideas. Suffering from depression and exhausted by decades of intellectual combat, he took his own life in 1906 during a family vacation in the Italian town of Duino. It was 3 years before Jean Perrin's experiments on Brownian motion would provide definitive evidence for the existence of atoms, confirming everything Boltzmann had fought for. The tragedy of his death is a reminder that even in science, being right is not always enough. The second law says that entropy tends to increase, and Boltzmann showed why. It is not that the universe is driven toward disorder by some mysterious force. It is that disordered states are overwhelmingly more probable than ordered ones. If you shuffle a deck of cards randomly, you will almost never produce a perfectly ordered arrangement, not because the laws of physics forbid it, but because there is only one such arrangement out of the roughly 8 times 10 to the 67th possible arrangements. Disorder is not a destination. It is a statistical inevitability. In 1927, the British astrophysicist Arthur Eddington gave this asymmetry its famous name. He called it the arrow of time. Eddington had a gift for vivid expression, and his description has endured. He said that if you draw an arrow arbitrarily, and if following the arrow you find more and more of the random element in the state of the world, then the arrow is pointing toward the future. If the random element decreases, the arrow points toward the past. And he famously added that the law of entropy increase holds the supreme position among the laws of nature, saying that if your theory is found to be against the second law of thermodynamics, there is nothing for it but to collapse in deepest humiliation. The arrow of time is what distinguishes the past from the future. It is why eggs break and never unbreak, why ice melts in warm water and never spontaneously forms, why perfume diffuses through a room but never collects back into the bottle, why your desk becomes messier over time and never tidier unless you exert energy to clean it, which increases entropy elsewhere. It is, in the most fundamental sense we know, the reason time seems to have a direction. But here is the deep puzzle that has haunted physicists for over a century: the fundamental laws of physics, the equations that govern the motion of individual particles and the behavior of fields, are almost entirely time-symmetric. They work equally well whether you run them forward or backward. If you filmed a collision between 2 billiard balls and played the film in reverse, the reversed collision would also obey Newton's laws perfectly. The equations of electromagnetism, of general relativity, and of quantum mechanics all look the same if you replace the time variable with its negative. At the microscopic level, there is no arrow. The laws of physics do not know which direction time runs. So where does the arrow come from? How do you get irreversibility from reversible laws? This question has been debated since the days of Boltzmann himself, and the most widely accepted answer points not to the laws, but to the initial conditions of the universe. The Big Bang, roughly 13.8 billion years ago, produced a state of extraordinarily low entropy, a hot, dense, astonishingly smooth and uniform starting point. From that starting point, entropy has been increasing ever since, and it is this increase that gives time its apparent direction. We remember the past because our memories are physical records, correlations between the states of neurons in our brains and the lower entropy states of the universe that produced them. We cannot remember the future because the future has higher entropy, and the kind of systematic correlations that constitute memories do not form between present brain states and higher entropy future states. The arrow of time, then, is not written into the fundamental laws. It is written into the boundary conditions, the initial state from which the universe began. And in the block universe picture, this initial state exists alongside all other states. The arrow does not emerge because time flows from past to future. The arrow is simply a pattern embedded in the block, a gradient of entropy running from one end to the other, like a temperature gradient running through a metal bar. The gradient is there. It is a real feature of the block, but nothing is flowing along it. If this picture seems disorienting, if the idea of a frozen universe with an arrow that points but does not move leaves you grasping for something solid, you are not alone. The tension between the timelessness of fundamental physics and the vividness of our experience of time has haunted physicists and philosophers for generations. And nowhere is this tension more acute, more painful, and more potentially productive than in the quest to unify Einstein's general relativity with quantum mechanics. General relativity, as we have seen, describes gravity as the curvature of four-dimensional spacetime. Quantum mechanics describes the behavior of matter and energy at the smallest scales. Both theories are spectacularly successful in their own domains, confirmed by experiment to extraordinary precision. But they are fundamentally incompatible with each other. General relativity is a theory of smooth, continuous geometry. Quantum mechanics is a theory of discrete, probabilistic events. When you try to apply quantum mechanics to spacetime itself, to treat the geometry of the universe as a quantum object, everything breaks down. The equations produce infinities. The predictions become meaningless. For most of the 20th century and into the 21st, physicists have been searching for a theory of quantum gravity that could unite these two pillars of modern physics. And one of the first and most striking results of this search was the discovery that when you try to quantize gravity, time disappears entirely from the fundamental equations. In 1967, the American physicist Bryce DeWitt published a remarkable equation that would bear his name, along with that of John Archibald Wheeler. The story of its origin has the feel of a legend. In 1965, Wheeler had a 2-hour layover between flights at the Raleigh-Durham Airport in North Carolina. He called DeWitt, who was then at the University of North Carolina in Chapel Hill, and proposed that they meet at the airport to discuss physics during the wait. de Witt arrived with the Hamilton-Jacobi equation of general relativity, a classical equation that describes how spacetime geometry evolves. He suggested to Wheeler that they could quantize it in the same way that Erwin Schrödinger had quantized the hydrogen atom decades earlier, by replacing certain mathematical quantities with quantum operators. Wheeler was electrified. He declared on the spot that the equation for quantum gravity had been found. The resulting equation, the Wheeler-de Witt equation, describes the quantum state of the entire universe. It is meant to be the Schrödinger equation of quantum gravity. There is just one problem, and it is not a small one. The equation has no time variable. In ordinary quantum mechanics, the Schrödinger equation tells you how a quantum system evolves over time. Time is right there in the equation, front and center, ticking along like a metronome. The wave function changes as time passes. Probabilities shift. Outcomes unfold. But in the Wheeler-de Witt equation, the Hamiltonian operator acting on the wave function of the universe equals zero, not close to zero, exactly zero. The state the equation describes is perfectly static. Nothing evolves, nothing changes. The wave function of the universe just sits there, motionless, for all eternity. This is known as the problem of time in quantum gravity, and it remains one of the deepest unsolved problems in all of theoretical physics. It suggests that at the most fundamental level of description, at the level where quantum mechanics meets gravity, there is no such thing as time. Time is not a fundamental ingredient of reality. It is something that must emerge, somehow, from a deeper, timeless substrate, the way temperature emerges from the random motion of atoms, or the way wetness emerges from the properties of water molecules. Carlo Rovelli, one of the founders of loop quantum gravity and the author of The Order of Time, has written extensively about this problem. Rovelli argues that time, in the fundamental equations of the universe, does not exist. What we call time is a macroscopic, thermodynamic, perspectival phenomenon. It is not a feature of the fundamental laws, but an artifact of our particular location in the universe. Our size, our speed, our sensitivity to certain patterns and insensitivity to others. At the deepest level, Rovelli suggests, the universe is not a story unfolding in time. It is a network of relationships between events, a web of correlations, and there is no clock ticking in the background, no river flowing from past to future. Rovelli's view has a beautiful and somewhat melancholy quality to it. He compares our experience of time to the way we experience heat. When you touch a hot stove, you feel a burning sensation. That sensation is real, vivid, and immediate. But physics tells us that there is no such thing as heat at the fundamental level. There are only molecules in rapid motion. The burning sensation is something your nervous system creates in response to a particular kind of molecular agitation. It is not a property of the stove. It is a property of your interaction with the stove. Time, Rovelli suggests, is similar. The flow of time is not a property of the universe. It is a property of our interaction with the universe, a feature that emerges when a particular kind of system, a brain, a thermodynamic engine, an entropy-producing observer, interacts with the rest of reality in a particular way. This perspective is reinforced by the way time appears in different formulations of physics. In Newtonian mechanics, time is an absolute external parameter, ticking in the background. In special relativity, time becomes relative, different for different observers, but still present in the equations as a coordinate. In general relativity, time becomes dynamic, warped, and curved by matter and energy, but still part of the geometric fabric of spacetime. But in canonical quantum gravity, in the Wheeler-DeWitt equation and its descendants, time vanishes altogether. It is as if physics has been on a centuries-long journey of progressive dethronement, gradually stripping time of one privilege after another. First, its absoluteness, then its universality, then its fixedness, and finally, its very existence. The physicist Klaus Kiefer, who has worked extensively on the semi-classical approximation to quantum gravity, has explored how the familiar experience of time might emerge from the timeless Wheeler-DeWitt equation through a process analogous to the way classical physics emerges from quantum physics in a semi-classical approximation, when certain quantum variables are large enough to be treated approximately as classical. Time re-enters the picture as an approximate, emergent quantity. The universe, at this level of description, appears to evolve. Clocks appear to tick. Events appear to unfold in sequence. But this appearance is an approximation, valid only in certain regimes and from certain perspectives. At the deepest level, the timeless equation remains sovereign. Perhaps the most radical response to the problem of time came from a physicist working entirely outside the walls of any university. Julian Barbour earned his doctorate at the University of Cologne in 1968, studying the foundations of Einstein's general relativity. Then, he did something almost unheard of in modern physics. He left academia entirely, settled in a farmhouse near the village of South Newington in Oxfordshire, England, and spent the next several decades supporting himself and his family as a translator of Russian scientific papers, while pursuing, on his own time and at his own expense, research into the deepest questions about the nature of time. In 1999, after decades of solitary work, Barbour published a book called The End of Time. Its central argument was as simple as it was staggering. Time does not exist, not even as an emerging illusion, not even as a macroscopic approximation. There is no past, there is no present, there is no future, there is no flow, there is no change, there is no motion. All that exists are what Barbour calls nows, static configurations of the universe, frozen snapshots that are not ordered in time and not connected by any temporal process. Barbour's universe, which he named Platonia after Plato's realm of eternal and perfect forms, is a vast, timeless space of possibilities. Each point in Platonia represents one possible configuration of all the matter in the universe. The universe does not move through Platonia from one configuration to the next. There is no movement. Instead, certain configurations, certain nows, are more probable than others, and the nows that are most probable are the ones that contain within them structures that Barbour calls time capsules, patterns of information that look exactly like records of a past. Consider what this means. Your memories, the patterns of neural activity in your brain that feel so vivid and immediate, are not records of events that actually happened in a temporal sequence. They are patterns encoded in the configuration of your brain right now, in this single, frozen, timeless now. They look like records of the past. They are internally consistent in a way that creates the overwhelming impression of a continuous personal history. But there is no history. There is only this now, with all its embedded structure and all its apparent evidence of time having passed. Barber has drawn an analogy to the frames of a movie. Imagine taking a roll of film, cutting it into individual frames, and scattering those frames on the floor of a vast warehouse. Each frame is complete in itself, a single static image. None of them is moving. None of them is connected to any other by a thread of causation or temporal flow. And yet, each frame contains within it visual information that, to an intelligent observer examining that single frame, would strongly suggest a past and a future. A frame showing a ball in midair, for instance, contains within it the visual cue of a blur, suggesting motion, and the spatial context of a hand below and a target above, suggesting a throw that happened and a catch that will happen. But no throw happened. No catch will happen. There is only this frame with its suggestive internal structure. Barber argues that the universe is like that warehouse of scattered frames. There is no projector running the film. There is no sequence. There are just the frames themselves, the nows, each one containing within it the patterns of information that create the impression of a past, a future, and the passage of time between them. The projector, the sense of temporal sequence, is something that exists only in the experience of conscious beings whose brains happen to be time capsules. This is a deeply unsettling idea, and Barber is fully aware of its strangeness. He has written that he takes the perfectly conventional realist view that the external world exists, that there are genuine physical configurations of matter out there. He is not a solipsist or an idealist. He is not saying that the universe is a figment of our imaginations. He is saying that the universe is real, utterly real, but it is not what we think it is. It is not a story. It is a collection of moments, each as real as any other, none more current than any other. And the story is something we impose upon it. Barber showed that this framework was not merely a philosophical provocation. It was consistent with the mathematics of quantum gravity. The Wheeler-DeWitt equation, which describes a universe without time, was precisely what his timeless framework predicted. If you take seriously the idea that physics should be built from directly observable quantities, from the relationships between things rather than from an assumed background of absolute space and time, then the disappearance of time in quantum gravity is not a crisis. It is the natural and expected outcome. John Wheeler himself, the man who had declared the equation found in that airport meeting, responded to Barber's work with warmth and wonder. He said the book must have been fun to write because it was fun to read. But not everyone was won over. Not by any means. Lee Smolin is a theoretical physicist at the Perimeter Institute for Theoretical Physics in Waterloo, Canada. He is one of the founders of loop quantum gravity, a fearless thinker who has repeatedly challenged the orthodoxy of his field, and a brilliant communicator of complex ideas. In his 2013 book, Time Reborn, Smolin mounted a full-scale intellectual assault on the idea that time is an illusion. Smolin's argument begins with a startling admission. He confesses that for most of his career, he believed that time was unreal, that the block universe was the correct picture, that the flow of time was a cognitive illusion. But gradually, through decades of work on the foundations of physics, he came to believe that this view was not just incorrect, but actively harmful, that it was preventing physics from making progress on its deepest and most stubborn problems. Smolin argues that physicists have been seduced by the beauty and elegance of their mathematical models into confusing those models with reality itself. The equations of physics are timeless. They are written on paper in a language, mathematics, that is itself timeless and abstract. And physicists, Smolin says, have made the subtle but devastating error of projecting the timelessness of their equations onto the universe they are trying to describe. They see that the equations have no preferred now, no flow, no arrow, and they conclude that the universe has no preferred now, no flow, no arrow. But this is a category error. The equations are maps, not the territory, and just as a map of a city does not contain the smell of its bakeries or the sound of its traffic, the equations of physics may fail to contain time, even though the reality they describe is drenched in it. Smolin goes further still, into territory that many of his colleagues consider outright heresy. He suggests that the laws of physics themselves are not timeless and eternal, but may evolve over time. Since Newton, physicists have assumed that the laws of nature are fixed, that they were set at the beginning of the universe, and have remained unchanged ever since, like rules carved in stone at the foundation of reality. But Smolin asks where the evidence for this assumption is. We have never observed the laws of physics changing, true, but we have also never observed them being set. We have no explanation for why the laws are what they are, why the fundamental constants have the values they do, why the mass of the electron is what it is and not something else, and why gravity has the strength it does. In the block universe picture, these are questions without answers. The laws simply are. The constants simply are. They are eternal, unexplainable features of a timeless mathematical structure. But Smolin finds this intellectually unsatisfying. If the laws themselves could evolve over time through some meta-process not yet identified, then perhaps their values could be explained. Smolin has proposed a specific mechanism he calls cosmological natural selection, in which universes give birth to other universes through black holes, and the physical constants in each daughter universe are slightly modified over many generations. The laws evolve toward configurations that maximize black hole production, which happens to favor universes rich in complexity, chemistry, and the conditions for life. Whether or not this specific idea proves correct, the spirit behind it matters. Smolin insists that time is not the enemy of understanding. Time is the key to understanding. The flow of time is not an illusion to be dissolved, by elegant mathematics. It is the most fundamental feature of reality, the one from which everything else springs. The response from the physics community was mixed. Sabine Hossenfelder, a sharp-tongued theoretical physicist known for her impatience with empty speculation, wrote that while she enjoyed reading Time Reborn, she disagreed with virtually everything in it. Sean Carroll, a cosmologist at Johns Hopkins and a prominent defender of the block universe, has argued that everything Smolin attributes to the fundamental reality of time can be explained by the increase of entropy within a block universe. The flow of time, in Carroll's view, is not a fundamental feature of reality. It is a consequence of the special initial conditions of the Big Bang, the same conditions that gave us the thermodynamic arrow. There are other alternatives too. The growing block universe, first proposed by the British philosopher C.D. Broad in the 1920s, offers a middle path. In this picture, the past and present are real, but the future is not. The block of spacetime is not complete. It is growing, with new moments of existence being added at the boundary of the present. The future is genuinely open, genuinely undetermined, and the present is the leading edge of reality, the frontier where new existence comes into being. But the growing block has its own difficulties. It appears to conflict with the relativity of simultaneity, since it requires a universal now that serves as the boundary of the block, the place where new reality is being created. And as we have seen, special relativity denies the existence of any such universal present. Different observers in relative motion would disagree about where the boundary is, which leads to logical contradictions unless additional assumptions are made. The debate continues. It is one of the most active and contentious areas in the philosophy of physics, with new papers and new arguments appearing regularly. There is no consensus. What there is, though, is a remarkable and somewhat humbling fact. The most fundamental theories we have, our best and most successful descriptions of the physical world, both point, in different ways and for different reasons, toward a universe in which time is not what it appears to be. But perhaps the most surprising piece of this puzzle comes not from physics or philosophy at all, but from neuroscience. Because even if we cannot resolve the deep metaphysical question of whether time is fundamental or emergent, we can ask a more concrete and potentially answerable question. How does the human brain construct the experience of time? And the answer, it turns out, is stranger than almost anyone expected. The neuroscientist David Eagleman, who worked at Baylor College of Medicine and later at Stanford University, has spent much of his career studying time perception. His central finding is that the brain does not passively record the passage of time the way a stopwatch does. Instead, it actively constructs the experience of time from a complicated and somewhat unreliable patchwork of sensory data, memory, attention, emotion, and expectation. And this construction is remarkably easy to manipulate and distort, even under ordinary conditions. Consider the stopped clock illusion, something almost everyone has experienced. You glance at an analog clock, and the second hand seems to freeze for a moment, hanging in place just a beat too long before resuming its normal sweep. This is not your imagination. It is a well-documented perceptual phenomenon called chronostasis. When your eyes make a rapid movement, a saccade, to fixate on a new target, your brain fills in the brief gap between the end of the saccade and the arrival of the first clear image of the new target. It does this by extending your perception of the first thing you see after the saccade backward in time, making it appear to last longer than it actually did. The second hand appears to hang because your brain is retroactively editing your perceptual timeline. Or consider what happens during moments of extreme danger or fear. Many people who have been in car accidents, combat situations, or other life-threatening events report that during the seconds before impact, time seemed to slow down dramatically. Everything appeared to unfold in slow motion. Eagleman wanted to know whether the brain was actually processing information faster during these moments, like a camera shooting at a higher frame rate, or whether the sensation of slow motion was an illusion constructed after the fact. To test this, he designed an ingenious experiment. Participants were dropped backward from a 50-meter tower into a safety net, a terrifying experience by any standard. During the fall, they wore wrist-mounted devices that flashed images, alternating with their negative images at a speed just slightly too fast for normal perception. If the brain were truly running at a higher temporal resolution during the fall, participants should have been able to perceive these rapidly alternating images. They could not. Their temporal resolution was exactly the same during the fall as it was on the ground. The sensation of slowed time was real, but it was not caused by enhanced perception. It was caused by enhanced memory formation. During threatening events, the amygdala, the brain's emotional alarm system, triggers the formation of denser, more detailed memories. When the brain later reviews these unusually rich memories, it interprets their density as evidence that more time must have elapsed, because normally, denser memories correspond to longer durations. The slow motion experience is not a speeding up of the clock. It is a rewriting of the record. Even the ordinary experience of the present moment, that seamless, unified feeling of now, turns out to be a carefully engineered illusion. The brain faces a fundamental engineering challenge. Signals from different senses travel at different speeds and are processed in different brain regions at different rates. Light reaches your eyes almost instantaneously, but sound from the same event may take tens of milliseconds longer to arrive. Touch signals from your toes take significantly longer to reach your brain than touch signals from your face, because the nerves are physically longer, and once signals arrive in the brain, different sensory modalities are processed at different speeds by different neural circuits. If the brain simply displayed information as it arrived, your experience of reality would be chaotic. The sight of a friend clapping her hands would arrive before the sound, and the time gap would vary depending on how far away she was standing. Your experience of your own body would be fragmented, with sensations from your hands arriving noticeably before sensations from your feet. The brain solves this problem by waiting. It buffers incoming sensory information, collects signals from all modalities, and assembles them into a coherent, synchronized narrative slightly after the fact. Your perception of the present moment is not a window onto reality as it unfolds. It is a carefully edited, slightly delayed reconstruction of events that happened a fraction of a second ago. You are always living, in a sense, just slightly in the past. Eagleman has pointed out a startling consequence of this buffering process. Because neural signals from your feet take longer to reach your brain than signals from your face, a tall person may, in some measurable sense, live slightly further in the past than a short person. The difference is tiny, measured in milliseconds, but it is real. The brain must wait for the slowest signals to arrive before assembling the unified experience of now. And the longer the body, the longer that wait. There is another aspect of time perception that deserves attention here, and it has to do with the relationship between time and attention. Psychophysical experiments have shown that when you pay more attention to something, it appears to last longer. If you are shown a stream of identical images, and then a single different image, an oddball, is flashed for the same duration, the oddball appears to linger longer than the repeated images. This is not because the oddball actually lasted longer. It is because your brain devoted more processing resources to it, and the increased processing is interpreted as increased duration. This finding has led some researchers to propose what might be called the information processing model of time perception. The idea is elegant in its simplicity. The brain does not have a dedicated clock. What it has is an awareness of its own rate of information processing. When processing speeds up, as it does when attention is heightened, or when novel stimuli demand more resources, the brain counts more internal events per unit of objective time. And since it calibrates duration based on the number of events processed, it concludes, incorrectly, that more time has passed. The experience of time expanding or contracting is a direct consequence of the brain's use of information processing as a proxy for duration. This model explains a surprising range of temporal illusions. It explains why time seems to pass more slowly when you are bored, because boredom involves heightened self-monitoring and attention to the passage of time itself, paradoxically increasing the number of internal time-checking events. It explains why time seems to fly when you are engaged in a task, because attention is directed outward rather than inward, and fewer time-monitoring events are generated. It explains why childhood summers seem to last forever, because children encounter far more novel experiences than adults, triggering denser memory formation and a richer subjective record. And it explains why the years seem to accelerate as we age, because the proportion of genuinely novel experiences decreases, memories become less dense, and the subjective record of each year becomes thinner and more compressed. The implications of all this for the block universe are profound. If our experience of time is not a passive recording of an objective temporal flow, but an active construction, a model built by the brain from incomplete and sometimes misleading data, then the vividness of our temporal experience says nothing definitive about the fundamental nature of time itself. Our conviction that time flows, that the present is special, that the past is gone, and the future is yet to come, may be no more than the brain's best interpretation of the information available to it. And that interpretation, however compelling, is exactly the kind of thing that could be generated by a static brain embedded in a frozen block of spacetime. A brain whose neural architecture contains the right patterns of information to produce the illusion of motion without any actual motion occurring. Eagleman has observed that the days of thinking of time as a river, evenly flowing and always advancing, are over. Time perception is a construction of the brain, as prone to illusion and distortion as the sense of color or the sense of three-dimensional space. He suggests that as we come to understand time as a brain construction, we may eventually be able to untangle our perceptual biases from our physical theories, removing what he calls the most stubborn filter of all. This opens a tantalizing possibility. Perhaps the reason we experience motion, the reason time feels like it flows, is not because of anything happening in the external universe. Perhaps it is because of what is happening inside our skulls. The block universe may be frozen and static, but the brain embedded within it is a physical structure that encodes information about neighboring points along its world line. It contains patterns of neural activity that are consistent with a continuous personal history, with memories of a past and expectations of a future. And these patterns, these internal structures, are what generate the subjective experience of temporal flow. In Barber's language, our brains are time capsules. They are configurations of matter that contain records that look exactly like what you would expect to find if time had passed and events had unfolded in sequence, and perhaps that is all that is needed to produce the experience. Not actual motion through a temporal dimension, but simply the right pattern of information, the right arrangement of neurons and synapses, embedded in a single frozen moment of the block. If the block universe is correct, if all moments of time exist equally and eternally, then what does this mean for free will, for moral responsibility, for the meaning of our lives? This is where physics reaches its limit and philosophy takes over, and where opinions diverge so sharply that even experts who agree on the mathematics can disagree violently about the implications. Some philosophers, like Hugh Price, argue that we should accept the implications of the block universe with intellectual maturity. The arrow of time, Price suggests, is a cognitive projection, a feature of our minds that we mistakenly attribute to the external world. There is no deep mystery about why time appears to flow. Time does not flow. We only think it does. And recognizing this, far from being nihilistic or depressing, can be liberating. It frees us from the anxiety of a fleeting present and allows us to see our lives as we see a completed novel, as a whole, from beginning to end, beautiful or tragic, or both. Others find this deeply unsatisfying. The philosopher John Lucas has written that the block universe gives a deeply inadequate view of time, that it fails to account for the passage of time, the preeminence of the present, and the difference between the future and the past. These are not illusions to be explained away, Lucas insists. They are the most fundamental features of our experience, and any theory that dismisses them as mere appearances has, in some essential way, failed to describe reality as it is. The philosopher Karl Popper shared this unease. In conversations with Einstein himself, Popper argued against determinism and eternalism from a common-sense standpoint, insisting that the openness of the future was not merely a feeling, but a genuine feature of reality. Einstein, characteristically, was unmoved. He had the equations on his side, and for Einstein, the equations were the final arbiter. More recently, the physicists Avshalom Elitzur and Shahar Dolav have argued that certain experiments in quantum mechanics, including experiments involving quantum erasure and delayed choice scenarios, challenge the block universe picture directly. They contend that these experiments provide evidence of what they call an objective passage of time, a feature of reality that cannot be reduced to a static geometric structure. Their arguments remain controversial, but they represent a growing willingness among some physicists to question the eternalist consensus. And there is the concern about freedom. If the future already exists, if every decision you will ever make is already embedded in the block of spacetime as an accomplished fact, then it seems as though you have no genuine agency. Your choices are not real choices between open alternatives. They are fixed features of a predetermined geometry, no more alterable than the angles of a triangle. You could not have done otherwise. You will not do otherwise. Everything is already settled. This concern strikes at something deeply personal. When you agonize over a decision, weighing options, imagining consequences, and feeling the tension of uncertainty, that experience of deliberation feels real. It feels like you are standing at a crossroads with genuine paths extending before you. Paths that could lead to genuinely different futures. But if the block universe is correct, there are no crossroads. There is only the world line, already drawn, already fixed. And the feeling of standing at a crossroads is just one more feature of the block, as predetermined as everything else. Some physicists and philosophers have tried to soften this implication. The compatibilist position, which has a long history in philosophy, holds that free will is compatible with determinism, because free will does not require the ability to have done otherwise. What it requires is that your actions flow from your own desires, beliefs, and reasoning processes, rather than from external coercion. On this view, the fact that your decisions are embedded in the block does not make them unfree. They are your decisions, produced by your brain, shaped by your values and your reasoning. The fact that they were always going to happen the way they happened does not make them any less yours. Defenders of the block universe respond that this fear is based on a misunderstanding. The fact that your decisions exist in the block does not mean they were made for you by some external force. You still deliberate. You still weigh evidence and consider consequences. You still feel the pull of competing desires and the weight of moral obligation. The process of deciding is part of the block, woven into the fabric of your world line. Your decisions are real in the sense that they are genuine features of reality. They are just not temporally emergent. They do not come into being at the moment you make them. They have always existed, and they always will. the novelist Kurt Vonnegut, who was fascinated by the implications of the block universe, put it more poetically in his novel Slaughterhouse-Five. His character, Billy Pilgrim, unstuck in time, learns from the alien Tralfamadorians that all moments exist simultaneously, and that the illusion of free will is just that, an illusion. When someone dies, the Tralfamadorians simply say, "So it goes," because from their perspective, the dead person is still alive in all the moments they inhabited. It is, depending on your temperament, either the most comforting or the most horrifying idea imaginable, and perhaps there is genuinely something comforting in it if you allow yourself to sit with the idea long enough. If every moment of your life exists eternally, then nothing is truly lost. The joyful moments are not erased by the passage of time. They are preserved forever in the geometry of spacetime. The people you have loved and lost are not gone. They are still there in the moments you shared, as real and as vivid as they ever were. The block universe is, in this sense, a kind of monument to existence. Nothing that has ever been is forgotten. Nothing that has ever happened fades away. It all endures, etched permanently into the structure of the cosmos, beyond the reach of entropy and decay. Whether that thought gives you peace or fills you with existential dread probably depends on who you are and what you have lived through. The physics, as always, is indifferent to our feelings about it. Whether this distinction is meaningful or is merely a sophisticated way of surrendering to fate is a question that each of us must answer for ourselves. And so we arrive at the edge of what is known, at the boundary between established science and the deepest of open mysteries. The equations of our most fundamental theories, general relativity and quantum mechanics, both point toward a universe in which time is not fundamental. In relativity, time is a dimension of a four-dimensional block, and the flow of time is an observer-dependent construction. In quantum gravity, time disappears altogether from the most basic equations, and the state of the universe is eternal and unchanging. And yet, we experience time. We experience it with a vividness and immediacy that surpasses every other aspect of our conscious existence. The ticking of a clock, the aging of a face, the falling of rain, the beating of a heart, the ache of longing for a moment already gone. These experiences are undeniable. They are the very medium of our lives. And explaining how they arise, whether from the thermodynamics of entropy increase, from the information processing architecture of our brains, or from some as yet undiscovered feature of quantum gravity, remains one of the deepest and most beautiful open questions in all of science. Perhaps the answer lies in thermodynamics, in the extraordinarily special initial conditions of the Big Bang, in the relentless statistical march of entropy from rare ordered states to common disordered ones. Perhaps it lies in neuroscience, in the way our brains buffer sensory information, construct the feeling of the present, and interpret dense memories as extended durations. Perhaps it lies in some future theory of quantum gravity, a theory that will show us how time crystallizes out of timelessness, the way ice crystallizes out of liquid water. A phase transition from a symmetric state to a broken one. Or perhaps the question is subtly wrongly posed. Perhaps asking why we experience motion in a block universe is like asking why we see colors in an electromagnetic universe. The electromagnetic field has no color. Color is something our visual systems add, a way of encoding the wavelengths of light that stimulate the photoreceptors in our retinas. Red, blue, green, these are not properties of photons. They are properties of perception, and yet they are real, in the sense that they are genuine features of our conscious experience, even if they do not correspond to any feature of the external physical world. Perhaps time is the same. Perhaps the flow of time is the brain's way of encoding a fundamentally timeless reality, just as color is the brain's way of encoding a fundamentally colorless one. The philosopher Hermann, one of the great mathematical minds of the 20th century, captured this idea with haunting precision. He wrote that the objective world simply is. It does not happen. Only to the gaze of my consciousness, crawling upward along the lifeline of my body, does a section of this world come to life as a fleeting image in space, which continuously changes in time. Whale's image is beautiful and disturbing in equal measure. The world simply is. It does not happen. The happening is something consciousness adds. The flow, the motion, the urgency and impermanence of each passing second, all of this is the contribution of the observer, not the observed. The universe does not need time. Only we do. But this raises one final, haunting question. If consciousness is what animates the static block, if it is the crawling gaze of awareness that makes a frozen geometry feel like a flowing river, then what is consciousness? How does a particular arrangement of matter, a brain, a time capsule, a pattern of neurons and synapses, generate the inner experience of temporal flow? This is, of course, the hard problem of consciousness, the deepest puzzle in all of philosophy of mind, and it is connected, in ways that we are only beginning to glimpse, to the puzzle of time. Some physicists have begun to explore this connection directly. Roger Penrose, in The Emperor's New Mind and its sequel Shadows of the Mind, argued that consciousness is linked to quantum gravitational processes in the brain, specifically to the collapse of quantum superpositions in structures called microtubules within neurons. If Penrose is right, then consciousness and the problem of time in quantum gravity may not be separate puzzles at all. They may be two faces of the same mystery, two aspects of the same deep and still unexplored connection between mind, matter, and the structure of reality. We do not yet know whether Penrose is right about this. We do not know whether Barber is right about Platonia, or Smolin about time reborn, or Ravelli about the order of time. We do not know whether the future already exists, or whether it is being created moment by moment at the advancing edge of the present. What we do know is that the question, this most intimate and universal of questions, stands at the center of 21st century physics, philosophy, and neuroscience. It is a question that connects the largest structures in the cosmos to the smallest processes in the brain, the most abstract equations to the most concrete experiences, the impersonal geometry of spacetime to the deeply personal fact of being alive and aware and wondering. If so, then the question is not why we experience motion. The question is what kind of creatures we must be. what kind of brains we must have, what kind of evolutionary pressures must have shaped us in order for a frozen, timeless, four-dimensional block of spacetime to look, from the inside, like a rushing, flowing, perpetually changing stream of experience. And that question may be the most beautiful question in all of science. Albert Einstein died on April 18th, 1955, in Princeton, New Jersey, less than a month after his friend, Michel Besso, in his final letter to Besso's family. He had written that the distinction between past, present, and future is only a stubbornly persistent illusion. Einstein wrote those words with the confidence of a man who had spent his life studying the deep structure of reality and had found, at its foundation, a universe without time. Whether he was right, whether the cosmos is truly a frozen block or a flowing river, or something stranger than either of those familiar metaphors can capture, remains one of the great unresolved questions of human understanding. It is a question that lives at the intersection of physics and philosophy, of mathematics and consciousness, of the deepest equations we have ever written, and the most personal experiences we have ever known. The answer, whatever it turns out to be, will reshape our understanding of what it means to exist. It will change how we think about memory, about death, about destiny, about the nature of the self. And perhaps that is why this question, more than any other in physics, refuses to stay confined to the chalkboards and journals of specialists. It keeps reaching out through the equations and the thought experiments and the philosophical arguments to tap each of us on the shoulder and whisper, "What are you? What is this moment? And where in the great geometry of existence do you actually stand? You have been watching, and I am grateful you stayed for this journey." If this exploration of the nature of time and motion left you thinking, left you with a different relationship to the clock on your wall, or the memory of yesterday, or the uncertainty of tomorrow, please consider subscribing and leaving a like. It helps us reach more people who care about these questions. And drop a comment below. Tell us what you think. Is time real? Is the future already written? Or is there something that physics has not yet found the right words for? Thanks for watching. We will see you next time.